Hello, this is Laura Slaminsky, a teacher at Edina High School, and today we're going to look at Lesson 9, Logarithms. How many digits do you need? So this is going to show us a commonplace situation where we use logs. The class started today with a review of yesterday. You can see in opening exercise A, it says what power of 2 gives me 8. We're going to rewrite that as a log. It's log base 2 of 8. Equals, and then again, what power of 2 gives me 8, and it's 3. So 3 is your answer there. Again, the second one I could rewrite as log base 5 of 625. But again, the way I would talk about it is what power of 5 gives me 625, and the answer is 4. Also, as a reminder of yesterday, we can then convert that into exponential form. I could take a 5 to the 4th power equals 625. So that's called exponential form. So we want to make sure we can go back and forth between log form and exponential form, as you saw in your homework. As the lesson went on, we did do an exploratory challenge to introduce the lesson, but we're going to cut over to kind of what we found. And what we were talking about is how many characters you would need to make unique codes for different people in a club. What we found out through exploring is that you could make unique codes for 2 people with 1 letter. So for example, if I had person 1 was letter A, person 2 was letter B. As soon as we jump to 4 people in our group, we would need 2 letters to make unique codes. And you can see on the right hand side the options: 1 person could be AA, 1 person BA, AB, and BB. We continued in the exploratory challenge and found that 8 people needed 3-letter code. And so from here we started to recognize a pattern. When I look at it and I know that 2 people gives me 1 letter, 4 people gives me 2 letters, and 8 people gives me 3 letters, I started comparing these numbers. And what we found is that we could rewrite them each in kind of exponential, because I noticed that these are being multiplied by 2 over here. So these are all being multiplied by 2. So as a class, we figured out that, well, 2 to what power equals 8? Well, that's 2 to the 3rd, could represent the last one. And in the second one, 2 to what power equals 4? Well, that is the second. And 2 to what power equals 1? Well, that was the 0. Sorry. 2 to the 1 power equals 2. There we go. I did that backwards. Okay, so we figured out that we were kind of using the to the what power idea. So even though I was writing it in exponential here, as soon as we start asking ourselves what power of 2 gives me 8, what power of 2 gives me 2, what power of 2 gives me 4, we should start immediately thinking about logs. Another way to write this last problem would be log base 2 of 8 equals what? And we got 3. So when we were actually finding our answers, we were using that what power function, which is logs. So if we use that idea and we move on to part C, and this is complete the following statement and list the secret ID codes for 16 people. Okay, so again, I'd be asking myself, what power of 2 gives me 16? Which again, now we will write with logs. Log of base 2 of 16 equals, and again, I know 2 to the 4th power equals 16. So my answer for this one is 4. All right, so then we continued on, filled in the table, and really, again, what we found is that we can use the log function to write this pattern. Okay, and so as we were writing it, we were writing, for example, log base 2 of 16 equals 4. We're going to take that last example where this was the A and B. So it's the number of different letters, or it could be numbers, that we're using to make the code. The 16 is the number of people in the group. I don't know why that always changes over. And finally, the 4 is the number of characters or digits in the code. That's the number of things I need to make the unique codes. And what we'll see throughout this lesson is that this idea carries over for all sorts of different things. When we want to figure out how many digits or how many characters we need to make unique things for people, it really is using the log function. So as we look at the exercises, it says when Autumn's club grew to include more than 16 people, she will need 5 digits to answer a unique ID code for each number. And the question is, what is the maximum number of people that could be in the club before she needs to switch to a 6-digit code? Now, when I think about this, we know that it's the idea of, so 2 to the 5th power, okay, so the 5 is the digit code, equals 32. And if I was to do 2 to the 6th power, it equals 64. Now we could use logs in this case, so it would be log base 2 of 32 equals 5, log base 2 of 64 equals 6. But actually in this one, because of the way we're thinking about the problem, a lot of my students thought it made sense to write it in exponential form first. And as we can see, the maximum number of people that we could have before we need to switch to a 6th digit would be 32. Okay, so as soon as it grows to more than 32 people, I need to switch to 6 digits. As soon as there are more than 32 people, I need 6 digits. Okay, the other thing you could say in this case is you could say the most people that could use 5 digits is 32. Obviously, you're saying the same thing. Number 2 says, if Autumn has 256 members in her club, how many digits would she need to assign each club member a unique ID of A's and B's? So again, the fact that I can only use 2 letters, I'm asking myself what power of 2 is 256. So as soon as I use that what power idea, log base 2 of 256, I ask myself what power of 2 gives me 256, and I get 8 as my answer. So 8 characters or 8 digits. Now this book uses digits in this case. I used characters because we're talking letters in this example, but I just want to make you aware that this curriculum kind of jumps back and forth between those two for the answer. So we can see that we can use this for multiple cases in Autumn's situation, but what I like about the next few examples is it extends it to some other real-world examples. So the next example says 1,000 people are given unique identifiers made up of the digits 0 through 9. How many digits would be needed for each ID number? Again, it gets confusing because they start using the word digits over and over again, so you really have to decipher what do you know. These numbers right here, 0 through 9, there's 10 numbers, 0 through 9. Again, that's the different things they can use within the code. So that's going to be my power, or my base, okay? The 1,000 people is how many I'm trying to get. And again, my answer is going to be how many spaces does my ID code need? So again, my question is what power of 10 gives me 1,000? So as soon as I say what power, I would do log base 10 of 1,000 equals what? And so again, I'd say what power of 10 is 1,000, and I get 3. So I would need 3-digit codes in order to make unique codes for those 1,000 people using 10 different numbers. Now this is a good time to talk about this very special case of when we have base 10. You might want to make yourself a note that we have this thing called the common log. If you see a log button on a scientific calculator or any more basic calculator, if you just put log, you'll see that it doesn't put a base at all. In fact, it will just say like log of x. Okay? Anytime there's no base there, that is a common log, and that means base 10. Okay? So a common log without a base implies that there's a base 10 there. You can write it in if you want to, but you don't have to, and it's important to understand that when you see textbooks or when you see math, if it's a common log, people will usually not put that base 10 there. However, we would still be asking ourselves in this situation, what power of 10 gives me whatever that x is? That's important to understand. Our next example here says there's approximately 317 million people in the United States. We're going to compute log. Again, there's no base here. So hopefully you're thinking about this common log idea. We're talking about log base 10. I'm going to rewrite it here. So it's telling me to compute log base 10. So you don't have to put that in there. And this one actually has 100 million. So we're asking ourselves, what power of 10 gives me 100 million? Again, the easy thing to do is to count up the zeros. We'll see that there's 8 zeros. So for 100 million people, remember this is people, I would need an 8-digit code. Having said that, we have 317 million people. So clearly 8 digits is not enough for a social security number. Okay? So the next part guides me and says, okay, now figure out the common log, or log base 10, of 1 billion. I'm drawing in my commas because I think it looks nicer. So when I ask myself, what power of 10 gives me 1 billion, I get 9 digits. So it's saying, explain why social security numbers are 9 digits long. Well, I need enough different combinations to be able to get me 317 million people. So if social security numbers were only 8 digits, I could only cover 100 million people, which isn't enough. And if I go to 9 digits, I can cover 1 billion people, which is plenty. So that's why our social security numbers are 9 digits long. And last but not least, the last example on the next page, number 4, talks about phone numbers. It says there are many more telephones than the numbers of people in the United States because of people having home phones, cell phones, business phones, faxes, etc. Assuming we need at most 10 billion phone numbers in the United States, how many digits would we need so that each number is unique? Okay, so for this, we are going to assume that we can use the numbers 0 through 9 for this problem. So again, I'm going to ask myself what power, so I'm using logs, because we're going to say each number can be 0 through 9. We're going to do log base 10, which we wouldn't have to put the 10 there. And then since we need 10 billion phone numbers, I'm taking the log base 10 of 10 billion. Whatever I get as my answer is the number of digits that we need in our phone numbers. So when I look at what power of 10 gives me 10 billion, I can count up the zeros and I see that it's 10 digits. And that is why our phone numbers are 10 digits. Now, having said that, it asks if it's reasonable. And again, we just created 10 billion phone numbers. In the previous problem, it said that there's 317 million people in the world, or in the United States, sorry, in the U.S. Having said that, if I divide those by each other, the number of phone numbers by the number of people, I get about 31 per person, 31 phone numbers per person. And again, obviously that seems pretty high. Having said that, we just said that we do need to account for multiple phone numbers per person, all of the businesses in the world, schools, whatever. So that's why that seems like a reasonable number, because it covers every person for multiple phones plus a lot of extras for all the other businesses. So that's the lesson for lesson number 9. Again, the focus is on being able to figure out how many digits you need to make unique codes for different things, such as security codes. We talked about social security numbers, telephone numbers, ID numbers, your school IDs. It's the same idea. So logs are useful to help us be able to figure that out. Thank you, and don't forget to do your homework.